So, welcome to this week's AI seminar again. So today I'm very happy to introduce Professor Bernhard Nebel. He's a professor at the University of Freiburg for the foundations of artificial intelligence. His research interests are automated planning, knowledge representation, and its application to robotics. He is an ACM, AAA, and a Euro AI fellow, and he's also a member of the German Academy of Science, Leopoldina, and a member of Academia Europea. In 2019, he was named as one of the 10 formative minds in German AI history by the German Computer Science Society. So let's welcome Professor Bernhard Nebel to introduce his talk on implicit coordination in multi-agent pathfinding.
Yeah, thank you for the introduction. First of all, I was asked to make some announcements. There will be more talks the coming weeks. So that's the advertisement part. And then, well, I'm very happy to be here. I gave my first talk when I was a PhD student 30 years ago, in 1984 here at ISI. And then the year later, I came back and spent 3 months here as an intern and worked on the Nigel system. I'm not sure whether it still rings some bells. No idea. Okay. But since then, I've done a lot of other stuff, and the talk I'm giving now is more about KR and planning. So it's about implicit coordination and multi-agent pathfinding. And well, the title already suggested it has 2 topics, namely one is how agents can achieve a common goal, and the other topic is how agents can move around in a spatial environment in order to reach their respective destination. That's the multi-agent pathfinding thing. Without colliding, of course, that's the main thing. And then, of course, how do these things fit together? Okay, so what is implicit coordination? Well, when you have a multi-agent system and it has to coordinate somehow in order to achieve its objectives, and you can do that explicitly. You talk with each other and then you negotiate what kind of things you are going to do, or you do it implicitly. Implicitly then means, well, you just do the things, and by doing things, you coordinate with each other. So if one agent takes a nail and the other one takes the hammer, then, well, they know what they are going to do, right? Hopefully, they put the nail into the wall. And, well, they don't have to talk with each other to do that because, well, just by doing, they coordinate. And this kind of implicit coordination that comes up very naturally when you do distributed multi-agent planning. Well, it means, well, you have all your agents and then they start to plan what they are going to do. And by doing so, they make assumptions about what the other agents could do. And when they don't want to communicate, well, they just make the assumptions and then they start to act. And so an implicitly coordinated plan is just a plan which contains actions of oneself, where I take the nail, and then the action of the other agents, well, the other agent should take the hammer. And, well, of course, that doesn't necessarily lead to a good result because, well, they might, the agents might have different assumptions, but, well, there are circumstances when it works out. Okay, that's implicit coordination. And I have a small example here. So we had one of your common household robots that should supposedly help you in your household, and we have the human who wants to hang up a picture at the wall. And well, what does he do in order to do that? He says, well, I want to hang up the picture at the wall. And by that, he makes the assumption that the robot hears that and then makes his own deduction, namely that he should bring a hammer so that the human then can use the hammer in order to fix the picture to the wall. And that all can be done without much communication. And I have a very impressive example here by Tomasello, where you have somebody who wants to put apparently some stuff into this cardboard, but the door's closed. And then this little guy, without having given instruction, opens the doors. And then, well, the human is able to complete the task. That I think is pretty amazing. So what you have seen here is this little guy who was watching, and then he recognized what goal the adult had, and then he adopted the goal to be its own goal as well. And that is the part Tomasello we're focusing on. He wanted to show that even very small humans can be altruistic. It's sort of built into us, for some of us. In any case, so but then there was some implicit coordination going on. So the kid went to the doors and opened them, and then he looked at the adult and was expecting that the adult then can finish the task by putting the stuff into the board. Okay, so I think that is pretty impressive, and would be great if we could do something similar to that. And of course, well, I think we are far away from this scenario here, but in a much more simpler scenario, we probably can do that. And the simpler scenario is mobile agents that move around in spatial environments. That is probably a lot of you know is one of the central problems you have in many applications. And here I have an example of an airport where you have the ground traffic, and the ground traffic has to be coordinated. Yeah. And then they move around, hopefully without any collision. This is these days done by humans, but of course, you can also do that automatically, well, in theory at least. Problem is how to do all the fine details, but yeah. Here we have another example. It's the so-called Flatland challenge, where you have trains with, and they have destinations, and all of them have to go to the destinations. And that would look like as follows. They run around, not colliding with each other again, and then reach their goals. Okay. So when you try to abstract that, coming as the computer scientists usually do, they try to get to the essence of the problem. You can describe that as a multi-agent pathfinding problem. And well, that is a problem where you have a set of agents, you have an undirected simple graph, and then the initial state is modeled by an injective function, which tells you which agents are sitting on which nodes. And you also have a goal state, which again is an injective function that tells you where the agents want to be in the end. And what you want to find is you want to find a sequence of movements that transforms the initial state into the goal state by movements of single agents without collisions. An example, here we have the square agent and the circular agents, and the square agent, he wants to go where the circle agent is. I have symbolized that with a small square here. And the circle agent wants to go to B2 here. Okay, can they do that? Is there a plan to achieve that? Yes, there is. And well, the circular agent can go to B2. And well, if he would be selfish, he would just stay there. And then they couldn't fulfill their common goal. But the circular agent is not selfish, so he gives way to the square agent, and then the square agent can reach, and the circular agent can reach its goal, and they are all happy because everybody has now achieved its goals. okay, that was something we can centrally plan. So if we are God, we can say, well, you go first and you go second and so on. Of course, they also can do that for themselves, and that's what we will look at. And here in this example, we also only had single actions, but we can also have actions in parallel. So that's very well researched problems, both from a theoretical side, but also from the algorithmic side. So what we know since '84 is that finding out whether there exists a plan, a feasibility problem, that is a polynomial time problem. And we also know that the plan length can be bounded by cubic length, cubic many actions, when you have an undirected graph. How many years later? 36 years later, I solved the problem for directed graphs, which was sort of ignored or unsolved at least. So I came up with a solution and showed that then the problem becomes NP hard, and it's not completely clear whether it's also NP complete. But that is just a side note that's not relevant for the talk here. Deciding the bounded existence problem, which is which corresponds to the optimization problem. That is NP complete if we have an undirected graph. That was also shown in '86 already. And since then, a lot of different algorithms have been developed that are either optimal, suboptimal, guaranteed suboptimal, and so on. So we know a lot of it. We know how to solve these things, and we also have very fast algorithms for them. So now let's go one step beyond. And one step beyond is now that we say, well, we don't have a central plan anymore, but all the agents plan for themselves, and then they should get their act together by just doing implicit coordination, just by moving. And by that, then saying, by that, then expressing what they want to do, so the others can react to it. So what this means is that each agent generates a sequential plan, and it should be cycle-free, well, because cycles don't lead anywhere. And these plans should contain their own actions and also actions from the other agents, which is then an implicitly coordinated plan. And we will see some examples very soon. Joint execution is then that the agents do what their plan says. And if there's a conflict, so two agents want to act at the same time, then only one of them can do that. So they are chosen randomly if two of them want to act. And after an action has occurred, then the agents who have anticipated the actions of the other agents, well, they then can just continue with their plan. If this anticipation was wrong, then they need to replan and go on from there. Okay, so that's the execution model. Good thing is that by that, agents never end up in a dead end. And the reason for that is that all the agents always have a successful plan. So even if the anticipation was not right, well, there still exist another successful plan because, well, the other agents already plan for success.
Question?
Yes.
So if you go back to your very simple example where you had to have that one agent move out of the way for the other agent to get to its destination, I don't see why you would always have a successful plan there, right? Because there was no reason for that other agent to actually move out of the way.
Oh, there is a reason because the built-in thing is that they always want to achieve the common goal. The common goal is that everybody reaches their destination.
I see.
So that is given, that is set. Yeah.
Okay, I see.
Otherwise, you're right. Yeah. You have to have altruistic agents who support the others.
Got it.
Yeah. Okay, so what can go wrong? First thing that can go wrong is that agents are lazy. lazy means that sometimes they just choose a plan where they expect the other agent will act, where they could act. And a good example for that is when you have a dinner with your partner at home Sunday evening, and well, you're finished. So somebody has to make the dishes, right? So now you can come up with a plan. My partner does it. And what does your partner do? He comes up with the same plan. Both plans are successful if they are executed. But unfortunately, well, it means that everybody waits for everybody else. So it's a sort of a deadlock. It's not a real deadlock because we don't have resources here. But we wait forever for this plan to be successful. Okay. I call that the dishwashing dilemma. Of course, you can say, well, we don't want to have lazy agents. We want to have eager agents, agents that always act when they can. So when they act, when they make a plan, if it's possible that then they act in this plan as the first action. Okay, is that a good idea? Well, these deadlocks can be avoided, but the problem is that eager agents can do stupid things. So here we have an example where the square agent wants to go down, the circle agent wants to go up. Then they make plans and the square agent moves to the right. Then the circle agents also replans and goes to the right. And now the square agents who thought the circle agent would go the other way around, well, he thinks, okay, now I have to go back. And he goes back. And now the circle agents, well, he could now move up. But, well, he's an eager agent. He wants to do something. And, well, he does something and goes back. Well, that's stupid. But I've not said that eager agents are not stupid, right? So the thing is, now we are back to start and we have to think about what went wrong here. And well, what went wrong here is that eager agents, they just act without looking at what they are doing. So it's sort of an aimless activism. We know that from politicians sometimes, right? They also do something without getting closer to their goal. They just do something. And what we really want to have is we want to have optimally eager agents. So agents that plan to act first, but only if this is an optimal plan, if this is the shortest plan. And if we assume that we have optimally eager agents, then we are fine because then infinite execute are impossible. Well, they might come up with different plans, but all the plans have the same length. All of them are optimal, so they have to have the same length. And if and there must be one agent who wants to act. And well, after each executed action, well, the plan that is now the optimal plan will be one step shorter. And so when the agents replan, then they come up with, again, with a shorter plan. And so at finite number of steps, we will terminate. Okay, so what we have here is that implicit coordination works if we can observe the others and we assume that the agents all plan optimally.
So are you assuming that agents cannot interfere with your plan? Because I can see a case where another agent also acts and that interferes with your optimal plan, so now your plan takes longer.
No, well, no. I'm not looking for, so when I'm saying a plan of the agent, I mean the implicitly coordinated plan where we also have the actions of the other agents in there. So it's not your own actions only, it's the actions of all the agents which you plan.
Could you go back to the formal, that example you gave? Because I made it, the example of the eager agents stepping on each other's. So I understood your formalism earlier to say that each agent, as you said, has a plan for all actions of all agents.
Yep.
And whenever that action deviates from the pre-plan, they replan. But in that example you gave with the eager agents, it seemed like for the circle agent to move to the right, would deviate from the square agent's plan that the circle agent would have. So I guess I didn't understand that example. Wouldn't that cause a replanning for the eager agent? Yeah. So yeah. So you see that. So maybe go back a step, right? So when the square agent on top moves to V3, shouldn't the circle agent in V6?
Sorry.
Yeah, so you have that first move, and now the circle agent, I would imagine, would replan because this deviates from the successful plan that the circle agent has. So why doesn't the circle agent at this point replan and instead of moving to V5, move to V7? Maybe I misunderstood something about that.
Yeah. Well, maybe he replans, but he replans to go here again. And the replanning only involves the actions then of the square agent.
So the replanning, so what you just presented was that the optimality would try to create a short plan.
Yeah.
In this case, there's no guarantee of a short plan.
Right.
I understand.
So, yeah.
And also you're assuming that the agents don't communicate.
Yes.
Right?
Yeah. That's
Other than watching what the others do.
right. Yeah. So they don't communicate and they don't have this thing you would take as given that they that they go for an optimal plan or a cheapest plan or whatsoever. It's they just act and come up with a new plan, and that plan might be stupid because it might be long also. Yeah. So, but when you build in the optimality, then you are good because then things work as you would have expected. So it took us some time to come to this point. The interesting thing is then when you get one step further, which we will do in a minute, when you don't have full observability, then things are not good enough anymore. But before we go to that, so guarantee infinite. Yeah, so yeah, one problem is that the agents now, they have to solve a sequence of NP-hard problems. Well, we solve NP-hard problems in any case, well, sort of solving them. And so, well, let's look at what we have to do in the central case when we do central planning. Well, we just solve one NP-hard problem, namely the generation of a shortest plan for all the agents. And when we do this in a distributed fashion that everybody does planning, well, then each agent has to solve polynomially many NP-hard problems. So it's not one, it's polynomially many. But, well, the complexity class FP, functional polynomial within NP oracle, that is just the class that covers all that, right? Whether it's one or it's many cases where you have to call an NP oracle. So it is more difficult, but it's not really more difficult. It's all stays in this NP class. So then you might think about, can we do better with approximations? And well, unfortunately, they destroy the success guarantee because then, well, you can just move around without going to the goal. But maybe we can restore that to some degree. And well, we can do that by saying we want to be conservative. I think that's not very popular here in California. And I mean a particular technical thing with the conservatism. So conservative agents, they always replan from the initial state and include the already executed actions as a plan prefix. So why is that good? Well, it means that, well, when a conservative agent plans, he never run into infinite cycles because, well, he avoids the cycles that could be created because he sees what has been already done. So he cannot create a cycle there. Okay, this is good, but it can mean that conservative eager agents that not go for optimality, they might explore the entire exponentially sized state space before terminating. They just try out everything because, well, they are just eager and don't look for optimality. And here I have an example for that. So the square agent moves, and then the circular agent moves to the goal. And then, well, the square agents, because now we have a different situation, well, he can think, well, I go down again, and then he goes down, and then the triangle agent goes up, and then now the circular agent can go down again, because we don't have a cycle here yet.
Excuse me, there's a water bottle there for you.
Excuse me?
There's a water bottle at the counter for you. Water
Water.
bottle on the counter for
Just need
you.
water.
Me too.
Oh, thank you. Yeah. So, and what can happen is if the execution order is chosen according to a gray counter, which you might have learned in your computer science studies, then we visit the entire state space, which is exponentially sized. Okay, so now let's step up one thing further. And now we say, well, we have only partial knowledge. So all the agents know their own destination, but they don't know the destinations of the other agents. They might have an idea. It's not, but it's not clear where the other agents are going. And still, the common goal is everybody should arrive at their own destination. Sort of. So for each agent, there is a set of possible destinations, and this is common knowledge, but the particular goal of the agent, that is unknown. And the common goal is, as I said, everybody reaches their destination. And then, well, as said, we don't want to have any communication, but now we need one sort of communicative action, and that is the shutdown action that tells the others, now I have arrived at my goal, and I don't want to move anymore. And that is necessary because otherwise the other agents cannot know whether they have achieved the common goal. It models sort of multi-robot interactions or interaction with a human. And now I have a very small example, again, with two robots, where we have this situation. So we have a square agent now. And the square agent wants to go to V3, and it knows that the other agent either wants to go to V1 or V4. And on the other hand, the circle agent wants to go to V4, and it knows that S wants to go to V2 or V3. Okay, so now can they still achieve their common goal that everybody ends up in their final destination? Well, they can form plans again, implicit plans, but now these plans are a little bit more complicated. So let's assume S tries to plan to achieve the common goal. It means that he makes moves, and then he inserts, by making these moves, he empowers the other agent to come closer to the goal. And in order to do that, well, he must also plan for the other agent, for S, and he must shift his perspective. So he must step into the shoes of agent S and plan, and now he must plan for all the possible destinations of C, of the circular agents. So it is a branching plan now, where we have to make a plan for C to go either to V1 or to V4. And by planning now for S, we have to forget what our own destinations are, because S doesn't know the destinations of C. It's a bit complicated, particularly this forgetting thing, because now, well, we step into the shoes of another agent, and then we have to forget what we know for sure about us, because, well, the other agent doesn't know it. But yeah, it works. So here we have an example plan that is successful, where agent S, the square agent, starts by moving from V1 to V4, and then he shifts perspective into agent C, and then, well, we have either the possibility that C wants to go to V1 or to V4, and according to that, well, the further plan develops. And all in all, well, after a while, we are successful. So if you have worked with non-deterministic single agent planning, you might think that is familiar. You have branching plans or policies. And as in the case with non-deterministic single agent planning, we define here strong plans. And I-strong plans are plans which are cycle-free. They are always successful. That is, when you reach the leaves, then all agents have shut down and they are covering. That means all the combinations of possible destinations have been covered in all the branches. And if there's an I-strong plan, then we call this instance I-solvable. Okay. And now I have something for you to think about. So, well, first of all, a few more definitions. A plan is called subjectively strong if it's I-strong for some agent, and it's objectively strong if it's I-strong for each agent I. So now we have this situation here, and the question is, does there exist a T-strong plan? Oh, no, I gave you already the solution. Sorry. Sorry. Okay, you've seen it already. So why is there no T-strong plan, but there's an S-strong and a C-strong plan? An S-strong plan. What can S form as a plan so that then the plan in it is all successful? Very easy. S moves to B1 and then does the shutdown action saying, well, I'm at my final destination. Now we have the triangle and the circular agent left. And well, the triangle agent knows when he goes down, then he might block the destination V2, right? But when the circular agent goes first, then he goes to a B5, makes the shutdown action, and then the triangle agent can go to its own goal. And we are all done. And well, the square agent just can form this plan. I do my first move, and then after that, the circular agent goes to its destination here or here, and then the triangle agent can do its final move. So the problem with the triangle agent is, well, he doesn't know what the real destinations of the circular and the square agents are, right? And they could be here or here. And it could be that they actually cannot reach the destination because they have to cross. And so, well, the triangle agent doesn't have any clue what he has to do. But once one of the other agents start to act, then he's all good. Okay. So let me tell you something about the structure of these plans we have there. So one of the keys to understand these branching plans is that there are stepping stones. And well, a stepping stone for some of the agents is a state in which I can move to each of its possible destinations and then shut down. And after that, the rest can be solved. And that is, yeah, we can look at this example here again. What would be a stepping stone? Well, S could create a stepping stone for C by just going to B3 via V4. And after that, well, the circular agent can go either to V1 or V4, sorry. And then it would have reached its final destination. And after that, the entire situation can be solved, right? So now C can move to V1 or V4. So now we have Schrödinger agents. And after that, the circular agent can move to its destination. And actually, this is the key to understand what's going on with these branching plans. And well, we have formulated that as the stepping stone theorem. And that says, well, if you have a solvable instance, then there exists an I-strong plan, well, by definition. And well, the branching points in these plans are those utilizing stepping stones. So when you look then at all the branches, there can be only finitely many branching points above each other. It's not that there can be many, but there can be only a few. So the proof is very easy, and I give the proof by example. I love giving proofs by example. We have here the plan again, and here we have a branching point, which is not a stepping stone, because well we shut down here in this branch, but we don't shut down here. So this is not a stepping stone, and we actually can get rid of that. And the reason for that is, well, in the branch where we don't have a stepping stone, there must be down here somewhere again the split between V1 and V4, and after that we have then successful executions. And so we can get rid of the entire branch where we shut down early. And that gives us then a plan where we only have stepping stones as the branching points. And how many stepping stones can you have? Not more than you can have agents, right? Because, well, that's where you branch on. You branch on the destinations of the agents. And that means, well, when you look at the executions cost of such a branching plan and say it's the number of atomic actions of the longest execution trace, then you know, well, it's the depth of this tree is O to number of nodes to the power of 4. And the reason for that is, well, when you want to solve an ordinary multi-agent pathfinding problem, then it's cubic. And well, here you get then times the number of nodes again, because the nodes are an upper bound. The number of nodes are an upper bound to the number of agents. Okay, so now the question is, can we now apply the same thing as we did before with a fully observable case? If we have optimally eager agent, will they be successful? Turns out, unfortunately not. So we found a counterexample. And the reason for that is you don't have uniform knowledge. They can have different forms of knowledge, and then they don't have the same idea about what is optimal. And in fact, execution cycles can happen then. Again, we can use conservatism on top of the optimally eager agent. And then we fortunately have a guarantee of a polynomial plan length, and also we know that it will be successful. And this is good, but there is, of course, something you have to pay for that. And that is, well, now coming up with such a plan is a p-space complete problem. It's not any longer NP complete, it's now p-space complete. Okay, and with that, I come to the conclusion. And so implicit coordination is something which is a powerful coordination technique, and it also works sometimes perfectly, particularly when you have a fully observable environment. Well, then optimally eager agents will do that. If you try it out in environments where you don't have full observability, then you might run into problems, like in our MAPF DU problem. Well, we still know that we can guarantee successful and polynomially bounded plans, but only if they are conservative and optimally eager. And we know that generating these plans is p-space complete. So if you want to have a take-home message from this talk, One thing is implicit coordination works sometimes. Second thing is, maybe it's sometimes better to communicate because it can save you an awful lot of hassle, in particular, in our case, an awful lot of computation. When going down from p-space to NP is it helps you to make things more practical. And then there are a number of other questions you can ask. And instead of you asking to ask them, I'll tell you the questions. So one of the things is when you, all these results hold for undirected general graphs, what happens if you have planar graphs? What if you have directed graphs? I don't know. So one of the other things is, does the p-space hardness result also hold for solvability? I also have it, I only have it for optimal solvability. And how would more general forms of describing the common knowledge about destinations affect the results? I don't know. Can we give similar results if you change the execution semantics? I don't know. It's very difficult because then this notion of stepping in the shoes of another agent doesn't work anymore that well. And one thing we are working on is whether we could be more aggressive in expectation about possible destinations, which means that you use notions like forward induction from game theory, where you assume that the actions of the other agents in the past were rational. So currently what we are just doing is we look at the agents, and if they do something we didn't anticipate, well, we replan without taking into account what the other agents did. And this is sort of stupid because, well, when they did something, they probably had a good idea what to do. And well, this idea might give us hints in the sense that, well, they knew that they could solve the problem, for example, where we thought it's unsolvable. And if the other agent did something, then we know that the problem must be solvable, and then we could use that. So that is something also in game theory people have looked at, and it's called forward induction. Unfortunately, that is not a concept that is precisely defined. It's more like a notion you can apply. And then, of course, there's a question of whether the other forms of implicit coordinations are possible, in particular when you have competitive scenarios. Okay, and that's what I wanted to tell you. And now you can also ask, why is no machine learning here? Yes.
So this was great. We do work on collaboration, particularly collaborations between scientists. And one of the challenges is that they don't know the landscape of what needs to be done. So in your case, it would be kind of like the agents can't see the whole map or the whole graph, right? So I wonder if you've considered, you know, the agents could communicate to each other what they know or what they see needs to be accomplished. Something about exchanging information makes the
that would be a great generalization of this thing. So that you, first of all, here you only have incomplete knowledge about the destination, but if you have incomplete information about the graph itself, and then either you can communicate or, well, you explore, or you, would be a great thing. And it would fit into this framework, but I think it would be, challenging.
I think Sven has a question. Yeah, online.
Yes, so I guess on real robots, sometimes things go wrong, right? They want to move to one cell and they move to an adjacent cell instead. So have you thought about, to which degree your guarantees continue to hold if these kinds of mishaps can happen?
Can you say it again?
So,
I didn't get the body,
So I was saying that, on real robots, things can go wrong, right? I mean, the robots want to move to a certain cell and they end up at an adjacent cell, for example. And I was wondering to which degree your guarantees continue to hold even in the face of that kind of uncertainty.
Good question. That means I haven't thought about it, and yeah. So you mean it's only uncertainty about the movement, but the observations are all fully observable. Also everything is fully observable, for example.
Well, I guess one needs to start sort of somewhere, right? You probably don't want to assume that everything is uncertain. So what are the sort of some of the assumptions that you can make about what is uncertain, so that you still, can apply some of your techniques?
I would have to think about it, but yeah, I think in general, you still can apply the techniques. And so in particular, if you have full observability, then in the case, so that was the first scenario, right? So everything is observable, you know where you want to go, and everybody else knows where you want to go. And then all of a sudden somebody makes a wrong move. Then, of course, the plans are not optimal any longer. The real plans are not optimal any longer. But, oh yes. So I think you cannot guarantee success anymore on that. But the deeper reason for that is you can make a mistake infinitely often, right? It can. So if a robot makes one mistake moving to a cell, then it can make that again in another situation, and then it might actually oscillate between two cells. So you don't have a guarantee anymore there.
Well, the probability of that might go to 0, right? But
yeah. Then it's similar to what is it? Strongly cyclic plan or something like that, right?
Yeah. Anyway, it's just something to think about.
Yeah. But yeah, I guess the thing that also observations are uncertain, that makes the thing much more challenging. Okay. Yeah. Yeah. Okay.
Sorry.
Yeah.
So I was wondering if, how robust this is to the existence of an adversary in one of, if you have an agent that tries to make sure that the plan does not succeed and everyone else is trying to succeed. So is there any way that the guarantees can still hold in that case?
Yeah, that was one of the later questions, right? I asked myself, can there be any sort of implicit coordination when you have a competition or not common goals? I have no idea. Yeah, there should be something, but I guess in game theory, what you do is you can give guarantees about that games can be won by one agent or not. Right? That is sort of what you would do there. Yeah.
So I'm so intrigued about the impact of the ability to communicate between agents, because there is some communication going on. I mean, obviously, even at the lowest level, an agent sees what the other one did, right? They may not know what their plan was, but they did see their most recent action or whatever action they've taken. So have you looked at, different levels of potential communication, starting from just what they have now, where they can just see, and up to transmitting the whole plan, right? And trying to coordinate that. I would think that different abilities to communicate at different levels would have a big impact on the ability to achieve the solution.
Yeah, that could very well be. So other people who work in this, what is it called? These MDPs that are also communicating and work in parallel. They have usually some sort of communication protocol they
Right. I mean, just offhand, and I haven't
Yeah.
thought about this much, you could see
Yeah.
the lowest level is just seeing what an agent did. One level up would be an agent saying what their next move is going to be, as opposed to their whole planned solution. And that would clearly impact what's going
Yeah.
on.
So yeah,
these
so actually,
examples.
we did it at some point where we said, well, what is sort of annoying is that these agents, they form their plans, and then one of them is said to execute an action, then the other is said to be execute an action, and that creates a lot of chaos because, well, these plans might not be synchronized or not compatible. And so we said, well, let's say that they can hand out tokens that are allowed, and this token allows you to execute as long as you want, and then you pass on this token.
Mhm.
And that makes things a lot more easier, and you can, in many more situations, achieve the common goal. Yeah. So that was along the line you said, yeah. But yeah, otherwise we didn't have any. We didn't look at many things or what communication could help.
Mhm.
But so yeah, another thing. So this thing I showed you, that was started out as an introductory example to a paper on our epistemic planner, dynamic epistemic planner. And then it got rejected. The reason was, well, is that now a paper about multi-agent pathfinding, or what can you do things much better? And then, well, we looked much more into this introductory example and worked it out. But behind all that is planning using dynamic epistemic logic, which is sort of very complicated model logic where you can also model communication. And in particular, you model epistemic states and how epistemic states change according to what people announce. Or so you could model that in this formalism, but we didn't look at it in this scenario.
I had two quick questions for the speaker. First of all, it's odd that you say that no communication is allowed here, because of course, the fact that agents can see each other means that agents implicitly have a way to communicate. One could imagine the agents engaging in some communication protocol where agents jiggle back and forth a little bit to communicate messages before they start moving to their destination. I guess question number one, has your analysis taken into account that in theory you can encode the agent's ability to observe each other allows them to encode messages to each other through the act of motion?
No, we didn't do that, and we didn't do that intentionally. So it's very similar to, do you know this game Hanabi? That is a game where you play together in order to achieve a common goal. And you only see you don't see your own cards, but you only see the cards of the other agents. So in such a game, you can come up with a protocol signaling what you mean when you do something, or you can have a number of agents that don't have a protocol beforehand. And then, well, they just have to rely on the notion that your fellow agents are rational. And that is what we wanted to have. We want only assume rationality and then see under which conditions can we achieve success. You're right. Moving around by itself, I think, is not communication. I'm not sure. I'm not a linguist. Maybe other people can chime in into that. But when you have a protocol you have negotiated about, then of course you can use movements as communication. But I think there's a difference between doing something and doing something to show somebody or to signal somebody something. When you do something not to achieve your goal, but in order to signal something, then I think this is communication. But otherwise, I wouldn't say it's not communication. But yeah, I guess that is a philosophical thing. Yeah.
And sorry, and then I had one more question. So oftentimes, of course, robots don't operate on general graphs, but they operate on these very highly regular 2D or 3D lattice graphs. And so my second question is, are there any important special cases of graphs where you can solve the MAPF DU problem in a lower complexity class?
Yeah, that is one of the open questions. So I don't know. Yeah. So I haven't found any class yet that allows the MAPF DU problem to be solved easier. But yeah, it doesn't mean that this class doesn't exist. Probably when you have a, what is a string graph. So a graph where all the nodes are just in a single line, then things are much easier. Or maybe even when you have a tree, then things might be much easier. But otherwise, yeah.
Danke, Professor, for coming here and speak with us. I have a question about SNCF and the other agents. I noticed there was a slide where you mentioned that they're communicating, but I didn't have a chance to note which agents, which countries they're based in. It was one of the slides earlier about.
I come a little bit closer because
you mentioned a slide with SNCF in France, the National Agency for the Rail.
Yeah.
But which of the other countries, agencies were on that slide? I was living in France before, so I took SNCF all the time.
DB is Germany, and I think there was.
Thank you.
I have to look it up. Yeah, it was Europe, and I think it's a contest that is going on at a number of planning conference, and I think also Sven Koenig there, he was quite successful in coming up with agents that are very good at it. DB, yeah, that's Germany. SCNF is France, and SB is Switzerland. Yeah.
Okay, thank you.
Yep. So at the very beginning, you showed implicit kind of communication in humans and helping, as well as the air traffic control scenario. And then, as you went through this, I was trying to relate this back to those. In implicit communication in humans, there's a lot of ambiguity. I might open a door for you, signaling that, I'm trying to help you put something in, but I may be also trying to get something myself or trying to get you to take something out. And even in the air traffic control scenario, mistakes are much more likely, or there may be delays in communication. So how would you kind of relate back the theoretical work you've done to those motivating scenarios?
So the air traffic control, that was just an example for multi-agent pathfinding. I'm not saying that they should do that with the implicit coordination stuff. So never do that. They should be centrally controlled. They should be centrally controlled. So no, these two examples were just examples for multi-agent pathfinding, and also I think the train example, that's also better done in a centrally controlled way. That is the implicit coordination in multi-agent pathfinding. That is, when you have robots that are from different suppliers, and well, they don't have any way to communicate, or you have a human in there, then of course, then you want to rely on coordination that is not pre-programmed or by a protocol or something like that.
Well, I mean, even with self-driving cars, right? If they're all from different manufacturers, they all have their own kind of autonomy system, and potentially they could do that type of observation and prediction. That seems like an example of something where you have the scenario, but I don't know what the affordances there are and whether,
Me neither. So I know a few people who work there, but well, actually, then also the execution model we have is sort of unrealistic because, well, with a car, you have continuous movements and, well, you would have to discretize that, but still it's in parallel. And then you need to have these observation parallel and think about what that means. And that is not covered in my framework.
There is one self-driving train in Paris. It leads to the SNCF station in Saint-Lazare. It's the fastest in Paris.
Where?
In Paris, there is
In Paris,
one
ah.
self-driving train.
Train, yes, yeah, the metro station. you mean, metro.
The 8 line in Paris. Yeah.
Yeah, but then this is also centrally controlled. Then. But most of the things are better centrally controlled because then you avoid all these problems you have when you don't have communication.
Right, I think we're about out of time, but let's thank the speaker.
Yeah, thank you.